Okay, minasan, konnichiwa, Samurai Engineer Test. So in this live lecture, we will proceed with the next topic about reinforced concrete, that is continuous reinforced structure. So this is a very short topic and very important one, and actually very popular in practice. Why? Because it's easier to use, and although it is just an estimate, it retains the accuracy and the level of precision that other methods is compared to other methods. So therefore, it is very popular with engineers even currently to use this method in order to come up with analysis or design. Although it is an estimate, it is also scientifically based on a theory of structure. So still, we'll have the theory of structure going into these formulas, and then some tweaks and an estimate or unestimated model of formula is suggested actually by the code. So without going into the details, please let somebody check our sound. So we are supposed to start 20 minutes ago, but I have misclick. Rather than live stream, I clicked the record. That's why after 20 minutes, I just noticed that I am not on live stream. That's why I adjust my setup. Then now here we are. Okay, thank you for confirming the clarity of sound. Shout out, Zairin. So let's proceed. So we have this topic, which is continuous reinforced concrete. So continuous, we already know we have the theory of structure. What do we need to imagine right now? Because anyway, during the construction of these structures, as much concrete as possible is placed in its pore. So meaning, actually, we would like this structure to be one pouring, but it is impossible. So we will going to pour it stage by stage. One reason that is impossible is the necessity of pulse work and form works, in addition to the necessity of what? Curing and drying. Okay? And also the setting up of reinforcements. So those major points and some others would likely will give us an stage by stage, pace by pace construction work. So for instance, the concrete for a whole floor or for a large part of it, including the supporting beams and girders and parts of the columns, may be placed at the same time. If we are going to decide about it, we would like to do it right like that. No? However, for example, the reinforcing bars extend from member to member, as from one span of a beam into the next, When there are construction joints, the reinforcing bars are left protruding from the older concrete, so they may be lapped or spliced to the bars in the newer concrete. Okay? So what happens? After some time, after curing of some other phase of the construction. Okay? So, in addition, the old concrete is cleaned so that the newer concrete will bond to it as well as possible. The result of all of this work is that RC structures are generally monolithic, right? Or continuous. Anyway, because it is the case in many occasions, okay, it is what? From the point of view of theory of structure, it is statically indeterminate. Okay, statically indeterminate. So there are three types of statically indeterminate structure in our theory. Okay? So fixed, continuous. Okay? So load placed in one span of a continuous structure will cause shear, moments, and deflection in other span of the structure. They depend on each other. Not only are the beams, okay, but the entire structure is also continuous. In other words, loads applied to a column affect the beams, slabs, other columns, and vice versa. Okay? General discussion of this method. In concrete design today, we use elastic method to analyze structure, and then with the factor or ultimate load, this procedure probably doesn't seem quite correct to the reader, but it does yield satisfactory result anyway. Okay? In the level that is still acceptable with regards to precision and accuracy. Okay? We might, for example, ask, why don't we use ultimate on inelastic analysis for reinforced concrete structure? The answer is that our theory and test are just not sufficiently advanced. I always repeat this. This is an open area for research. You have the opportunity to become a civil engineer and become interested, for example, in this area, and you can research about this and contribute to the current body of knowledge with regard to civil engineering. Take note, civil engineering is, I think, the second oldest, second or third oldest engineering profession in the world. Okay? Why? But the level of accuracy and precision is not just sufficiently advanced even up to this current time. Okay? So, we can do without the current suggestion from the code. So, many methods might be used to analyze continuous structures. The most common hand calculation is the moment distribution method. Recall, moment distribution method, MDM, or the modified moment distribution method, MMDM. So, we studied so many methods. When there are times, when there are opportunities where I handle theory of structures, I introduce 6 to 7 methods. Right? 6 to 7 methods. I am showing solution for every problem, 6 different solutions or 7 different solutions. Right? So, therefore, method is not a problem. For example, we we are having a matrix method, computer solution or numerical solution, okay? And others. So you can see we have been tabulated an iterative process in solving the indeterminate beams, for example. Whichever method is used, however, you should understand that to determine maximum shear and moments at different sections in the structure, it is necessary to consider different positions of the live loads. Okay? So we have to take note of the magnitude of live load and position it at the most critical location. Okay? Then analyze and solve problem. Okay? As a background for this material, a brief review of qualitative influence lines is given by this author, but I will not do it because that is theory of structure. Influence line is where we analyze the structure in terms of the moving load. Moving load meaning live load. Okay? Okay, so I will not do it right here. So that is supposed to be learned already from theory of structure like this. So these are the influence lines for shear, moment, positive moment, negative moment, positive shear, and negative shear. Okay. So these are the, take note of the what? The graph. When we have continuous, in this example, we have how many? 1, 2, 3, 4. There are 4. 4 spans. Okay? 4 spans. So you have to review it yourself because you already passed this subject. And take a look at this influence line for a moment in a frame like this, as much as for a beam. Okay? Just that was just shown, okay, a while ago. So like this, okay, load positions for maximum moment. In which span we must position the load, the maximum load, the live load, so that we will get the maximum moment. Okay, so we can do that. And just try to review that influence line topic, okay, on what? On our theory of structure. Okay. So let's go to the next topic, which is what? Limit design. Okay. So it can be shown that statically indeterminate beam or frame normally will not collapse when it is ultimate moment capacity. We know this because what? Continuous. Because what? Fixed. We are talking about what? Simple beam, usually determinate beam in our design. Okay? So its behavior is rather similar to the case where 3 men are walking along with a glove on their shoulders, and one of the men gets tired and lowers his shoulder just a little. The result is a redistribution of load to the other men and thus changes in the shears and moments throughout the log. Okay? So this is actually the explanation in the theory of structure, the actual explanation, same explanation that we have in theory of structure. Okay? It might be well at this point to attempt to distinguish between the terms plastic design as used in structural steel and limit design as used in reinforced concrete. Let us differentiate. In structural steel, plastic design involves a increased resisting moment, right, of a member after the extreme fiber of the member is stressed to its yield point. Right? Take note of this. Okay? Take note of this. I will just okay. What can you see? Letter A. Okay. Again, A and B. So when we are talking of steel design, again, the plastic region involves the increased resisting moment. Of course, because yield point is always what? Lower than the ultimate. And letter B, the redistribution, excuse me, or change in the moment pattern in the member. So there is a redistribution because if some portion of the element already collapse, then other portion will need to what help. Okay, just like the example of 3 men, wherein 1 man gets tired. Okay, the 2 men that are still working on carrying the log will but redistribute the existing load. Okay. Okay. LRFD is a steel design method that incorporates much of the theory associated with plastic design. So when we are talking of what? Steel design, LRFD is the name of the method. It is called LRFD. Okay. And however, in reinforced concrete, the increase in resisting moment of a section after part of the section has been stressed to its yield point has already been accounted for in the strength design procedure. Already accounted for. So there is no what redistribution, load. Therefore, limit design for reinforced concrete structure is concerned only with the change in the moment pattern after the steel reinforcement at some cross-section is stressed to its yield point. So the reaction. So when we are talking of plastic region, when we are talking of plastic region, the reaction of steel and reinforced concrete will differ in this manner, this particular manner as described. Okay? Take note. You have to repeat this, and repeat this, and repeat this so many times until you can get it, until you understand it. Okay? It's very important that you get this principle correctly. Okay? What do you mean? Okay. Again, there are 2 things when we are in the plastic region designing structural steel. There is an increased resisting moment of a member after the, take note, increased resisting moment even after the extreme fiber of the member is stressed to yield point. Okay? The distribution or change in the moment pattern of the member. Okay, so those 2 factors are involved. But in reinforced concrete, there is no more increase in resisting moment because it has already been accounted for previously in the strength design procedure. Therefore, the limit design for reinforced concrete structure is concerned only with the change in the moment pattern. So, supposed to be there are two factors, but now, since then the letter A factor is not present in reinforced concrete. Why? Why it is not present? It is present actually, but it was already been accounted for in the previous step. Okay? So included already in the design procedure. So you don't need to reassess, okay? Okay, or to make some modification in order to come up with the solution that would increase. You can get up an intermediate step that you can increase the resisting moment of the member. That is not allowed because it is already accounted for. Only the moment pattern is changing after the yield point is met. Okay, so the basic assumption used for limit design of reinforced concrete, therefore, for a plastic region is the ability of these materials to resist a so-called yield moment, while an appreciable increase in local curvature occurs. Local curvature. This is what we mean by angle. When we are talking theory of structure, this is angle. Okay? So you can use your diagram. So you can draw your force diagram. You can do your bending moment diagram. Then you have to draw your curvature diagram. Then you have to do your deflection diagram. So there are at least 4 diagrams that we need to draw in order to imagine the effect of the load. And also review what do we mean by plastic hinge, okay? Plastic hinge. Okay, so if one section of the statically indeterminate member reaches this yield moment and it begins to yield but does not fail. Okay, so rather it acts like a hinge. Okay, rather it acts like a hinge and throws the excess load up to sections of the members that have lesser stresses. So this is what we mean by redistribution of load. Okay, the resulting behavior is much like that of a log supported by 3 men when 1 man lowered his shoulder. Okay. So what will happen? Therefore, what we can expect? Therefore, we can expect this one, presence of plastic moment. Usually, we have to expect nominal moment. Okay? So, we have, therefore, the relationship of moment to the resulting curvature of a short length of a ductile member, the theoretical ultimate or nominal resisting moment of station is referred to as Mn. It's the same as plastic moment. So you can see here. Okay. Ideal, the yield, okay, is at this corner, then it is always equal. Okay? So, this is a moment curvature relationship. Now, that is the ideal. This is now the typical. Rather than ideal, rather than straight line, we have this actual or typical for reinforced concrete member. So, like this. Okay? So, the maximum here is the plastic moment that would equal to nominal moment. This part. Okay? So, what are the regions? First, cracking of concrete. So, here, about 1/2. Okay? About 1/2 of this. Then, first yielding of concrete. About on this corner. Okay? And then, here at the tail, that is the first crushing of concrete. So, first indication of cracking, yielding, and crushing. Okay? So, review also the collapse mechanism that we learned on theory of structure. This is how we know the collapse mechanism. Any book in theory of structure will have the collapse mechanism explanation. So, this is what we mean by collapse part. So, we model it like a hinge, plastic hinge. And therefore, instead of having a 2, we now have 3. Okay? Pin-like component. So, for example, instead of a simple beam, we have the fixed-ended beam. So, we have this. If we have the collapse mechanism on 1, 2, 3, on 3 points. Okay? So, we have the collapse mechanism on 2, in 1 point. So, okay. 1 point collapse mechanism. So, if we have fixed-ended beam, we have what? 3 collapse mechanism before it totally fail. Okay? So, indeterminate beam is a little bit, or it is stronger. Okay? It is stronger because, for example, fixed beam versus simple beam. It is stronger. So, we need to have 3 simultaneous collapse before it will fail. Okay? That is what we mean by that. For example, if we only have what? 1 fixed end and 1 pin end. So, we need 1, 2. We need 2 collapse mechanism, or we need 2 plastic hinges. Okay? So, as you can see, depending upon the type of structure, we can have a failure with 1 plastic hinge, with 2 plastic hinge, or with 3 plastic hinges. Okay? So, it depends upon the configuration. Okay? So, now take a look at the plastic. Okay. There. Okay. So, plastic analysis by equilibrium method. So, to analyze the structure plastically, it is necessary to compute the plastic or ultimate moments, okay, of the sections, to consider the moment redistribution after the ultimate moments develop. Okay. Take note always. After we reach yield point, then we are nearing the ultimate. Then after the ultimate, we will now have the what? Plastic. Okay? Development. And finally, to determine the ultimate loads that exist when the collapse mechanism is created. Okay? And if we design the load at that stage, then our structure better. It's a better chance of resisting the failure. Okay. The method of plastic analysis is known as the equilibrium method. So take note, when we say equilibrium method, we are actually using plastic analysis. Then we will explain it now, right now. Okay. For example, we have the fixed end beam of figure, this one. You can see on your screen. This is, for example, our given. For example, we have length 18 feet, span, fixed ended on both ends, PEM, okay, PEM, and PEM, then WK per foot. What do you mean by WK per foot? This is uniform load, kilopounds per foot. Okay? It is our desire to determine the value of nominal uniform load, the theoretical ultimate load the beam can support. How much? Okay? The maximum moments in the uniformly loaded fixed end beam in the elastic range occur at the fixed end. So let us compute the moment of fixed end beam. How? In theory of structure, this is how it looks like. This is how it looks like in theory of structure. Which one is higher? In the middle or at the support? So at the support, higher because it is fixed. At the middle, it is actually 1/2 the moment at the support. Okay? Okay? Do you follow? Do you follow? Okay, these are the formulas from theory of structure. Okay? So that is if the method of uniform load is increased, okay, method of uniform load, the moments in the beam will be increased proportionately until a plastic moment eventually develops, increasing this W. You have to continuously increase the W. What will happen here? It will increase. Okay? Because this is constant. L squared over 12 is constant. So, proportional increase will happen here. Okay? Proportional increase will happen in this portion at the support. Okay? As you increase, for example, you increase times 2. So, times 2 will happen here. Okay? That is what we mean by proportional increase. If you increase the load, okay, by times 3 will happen here. Times 3 will happen here. Times 3 will happen here. Clear? Are we clear? Do we follow? Okay? So, until eventually this system reach the plastic moment. Okay? So, meaning maximum. No? Okay? So, because of symmetry, plastic moments will be developed at the beam ends. At the beam ends. Why? Because they are fixed end beam and the higher moment will be or will occur on the support. Okay? So that's why plastic moments will first develop here. Okay? The beam will be unable to resist moments larger than Mn. So it will reach, as we go on increasing this value of load, this moment will go on until it reaches nominal load. Until it reaches nominal load. It will not go on over or greater than Mn. Okay? The maximum that it can resist is Mn. Okay? So can you imagine what's happening? Just for example, imagine Mn, nominal moment is 20. Imagine 20. And then when we have 2 kilopounds per foot, we just have what? For example, we just have 2 is the load. We have, for example, just an example, 2 times 18 squared over 12. So we can actually compute that. No? So 2 times 18 squared divided by 12. 54. Okay? So we have 54 here. Okay? The moment is 54. So if the maximum moment that is allowed is 20, just like what I've said, it cannot go on 54. It will only go up to 20 because that is the maximum. That is the maximum Mn. Okay? It cannot resist more than 20, for example. If ever, we are assuming that the Mn is 20. Okay? Or for example, let us assume another value. Assume 100. Okay? Assume 100. 100 is Mn. Okay? And then we get 2 kilopounds per foot. Then we have 54. Okay? 54. So still, our structure elastically can resist. Okay? Now, if we double this, it becomes 4. Okay? Then expect this to be double. 54 times 2 will become what? 108. That is what we mean by proportional. If we double this one, expect double. And you can test it in your calculator. Use your calculator. Substitute 4 times 18 squared divided by 12. That is 108. Okay, you can verify it in your calculator. Now, since the supposed nominal moment is 100, then it cannot resist the 108 anymore. It will only resist up to 100. What will happen to 8? Because 108 minus 100, that is 8. Okay? That is 8. What happens to the 8? The 8 will be redistributed on the other parts of this beam. Okay? How it would be redistributed? This is how it would be distributed. In this curve. In this manner. It is redistributed in this manner. Okay? This is the way it is redistributed. Talking of 8. Okay? Talking of 8. Okay? So that is how it works. Okay? Those points will rotate through large angles and thus the beam will be permitted to. What will happen here? Because it was already reached plastic region. What will happen? Instead of becoming the peaks, it will now start to become plastic hinge. This will now start to become plastic hinge. So you have plastic hinge here, you have plastic hinge here, then your beam is not fixed and beam anymore. Your beam is now simple support. Okay, do you follow? It becomes a simple support. But still, it is okay because this is 108, this is 54, this is 108, and this can still hold because it can hold the load up to 100, and right now it is only 54. Do you follow? So what happened is it became what? It became a simple beam. Okay? Okay, like this, okay? So this will happen. So this is fixed-ended beam. This is a fixed-ended beam, but after this end moment, this moment at the support reach the value Mn, so it become Mn, this will be converted to plastic hinge, so it will become what? Simple beam. Okay? Rather than fixed beam. But it's not yet failing. It will not yet fail. Because simple beam is a type of structure that can resist load. Okay? We can still resist the load because we are still what? Simple beam. Okay? Do you follow? What happened here? Okay. Okay. So deflect more and allow moments to increase out in the span. So although the plastic moment has been reached at the ends and plastic hinges are formed, the beam cannot fail because it has in effect become a simple end support beam for further load increase as shown. So actually it can still carry additional load for a simple beam. So we already finished with the fixed end beam, but we are starting just with the simple beam model. Okay? The load can now be increased on the simple beam and moments at the ends will remain constant. Remain constant up to what? 100. Because that is the supposedly the nominal moment. Okay? It will not go any further. Still, it will become 100. However, the moment out in the span will increase as it would in a uniformly loaded simple beam. This increase is shown by the dashed line in figure 411. Where is the 411? Here. Okay. This is the dashed line. Okay. So, this is our original PEM. The fixed-ended beam. This is our original fixed-ended beam. After these two become plastic hinge, we can increase the load and it will be carried by the beam like this. There is no further participation by the support because it will just what? Rotate. It is a plastic hinge already. So, the other parts of the beam will look like this. So, what I told you, the shape is like this. The distribution is the same shape like this. This is the redistribution of load. So the increase will go up until it reaches another value, which is what? Mn at the center. Okay? At the middle of the beam, it will become what? Mn. Before, again, because this point, the middle point reaches Mn, it will again become a plastic hinge. And now, this is the time that the whole structure will collapse. This whole element will collapse. Because we already have what? 3 plastic hinges. So 1, 2, and 3. So all of them, Mn, Mn, Mn. That is the time the whole beam will collapse. Okay? So how to compute? Therefore, one method of determining the value of Wn from this is to take the moments at the center line of the beam, okay? Knowing the moments there is Mn at collapse. So, Mn is equal to negative Mn. This is from the left side, okay? So, I will show you here. Here, this is our left side and right side. So, this is left side. Here, negative Mn. So, I am what? I am doing the RIPbE structure. So, negative Mn, okay, plus Wn L over 2 multiplied by WL over 2 minus L over 4. Okay? Okay? And then, let's what? So, that is the moment at the center. Then, simplify. So, simplifying, we will have this. Then, therefore, we can what? We can transfer this to the other side. It will become 2Mn. Mn plus Mn, 2Mn. And then, divide. So, 2 times 8 will become 16. And solve for Wn. So, therefore, 16Mn over L squared. Okay? So, whenever you are given a fixed end, you will have Wn looks like this. This is the formula. Okay? The formula. So, what happened? Any question? Do you have any question? Okay, just follow and use your calculator while we are talking about this. Okay. So let's move on to the next one. Okay. So you can even use superposition. Okay. Just like what we are doing in theorem structure using superposition. So this one is equal to this one plus this one. What is that? Separating the forces with the moment. So that we can what? Have a separate diagram for this type of forces, uniform load, and moment. Okay, so therefore, if you add these two, you will have this. So it is analytical in geometry, no? You can solve this by geometry actually. I am solving this by geometry sometimes. Geometry. Analytic geometry. So if you add this one to this one, it will become like this. And that's why you have what? Negative moment here, negative moment here, positive moment there. Okay? So again, if you do that, you can still have the same. This is the same as the previous derivation. We derive it here, so the same. But now we are we are finding out the value of Wn, but here we are finding out the value of moment rather than Wn. So this is the relationship between moment and Wn. So M is equal to W L squared over 16. Take note of this. Okay? So we will use that in order to estimate. So if we proceed with the same explanation, theory, okay? Determination of required MN from fixed beam with hinges forming mechanism. Okay? So for example, you have that. Okay? What will happen? MN going down, negative. MN going up, positive. So this is 2MN. Okay? So you can even use this very straightforward diagram. Okay? So the value of theoretical maximum concentrated load, if concentrated load is given rather than rather the Wn, okay, or uniform load, the beam can be determined by taking moments to the right or left of the load. Okay, right or left. Do not use both, just pick one. Okay. So because if you move from extreme to extreme, the answer would be 0 because that is static. Okay, static equilibrium. Okay, so just have to pick one. Just like on the moment, we analyze this. Okay, at the center line. Okay, at the center of the beam. We just do it from the center. Okay. Otherwise, if you do it from end to end, it will become 0. Okay. So, what do we have here? So this figure is the Hinge formation sequence in a prop up. So if you have a prop up beam, so you have this sequence. So prop up beam is 1 fix and 1 pin. So we need how many? We need 2 plastic hinge in order for this structure to fail. So we need first the plastic hinge at the support here, the fixed end, then we need another one at the center. So for example, this, okay, is MN, so it will be supported, resisted up to the value MN. Then afterwards, it cannot do anything anymore. So the resistance of the element will be redistributed like this. This is the original. And then the resistance will increase. This is what we mean by increase. Okay? The increased moment. Then now, there are now total of 3 plastic hinges. So it is initially having 1 hinge there. So we need another 2. So total of 3, then the element will fail. So what is now the suggestion of the code? So limit design under ACI code. So tests of reinforced concrete frames have shown that under certain conditions, there is definitely a redistribution of moments before collapse occurs. So it was proven. It was proven by testing. Okay? So even though some parts already transformed into plastic hinges, okay, it will still need to increase the moment. Okay, so up to such time that we have the maximum 3 hinges. So after 3 hinges, then the total, the whole element would fail. Okay, recognizing this fact, the ACI code permits factored moments calculated by elastic theory, not by an approximate analysis. Okay, elastic theory computation to be decreased at locations of maximum negative or positive moment in any span of a continuous structure for any loading arrangement. The amount by which moments can be decreased cannot exceed this value, 1000 E, or E is what? Epsilon. 1000 times epsilon. Okay, so meaning 10% with a maximum of 20%. So 10 to 20%. The distribution of moments as described herein is not permissible unless epsilon t is equal to or greater than 0.0075 at the section where the moment is reduced. Okay, take note, 10 to 20%. Okay, allowed. Okay, so 0.0075. Okay. If rho is greater than these values, redistribution is not permitted. So meaning it doesn't reach yet the condition that at least 3 portion of the structure reach plastic hinge mechanism. Okay? So values given in the table are for rectangular section with tensile reinforcement. So we have tables, for example, A.7, table B.7. Okay? So A.7 is actually, I think, this is the table for SIU for English units. B.7 is the table for SI units. Okay? So according to ACI section 18.10.4.1, negative or positive moments may be decreased for pre-stressed section using the same rules. Okay, so these are the commentary for the ACI. So let us take a look at figure 15. So we have here figure 15 here. Here, very important one. Okay. This figure is about maximum positive moments in end span. Okay, so we have what? 3 spans. So we need to put greater amount in this span 1 and 3 rather than span 2, because it would create a moment like this. The darkened lines, that is the moment due to loads given. What about the dotted lines? These broken lines represent adjusted moments permitted by ACI. So take note, this is the estimate, the adjustment ACI recommendation. Okay? Versus the moments due to load using the theoretical estimate, theoretical model, using the theory structure model. Okay? So this darkened area, okay, versus this one. So very nice graph, and therefore they said that it is acceptable. So these dotted lines as a model is acceptable. Okay. And here, letter C is what is about shear. Okay, so shear in this portion. So this arrow, shear going up, shear going down. So this is the moment. So the same what? In our textbook in theory of structure, the same, what do you mean by this? The same standard, the same direction, the same moment, what? Direction, like this, and like this, and for shear, the same direction, okay? Conventional, the same convention, okay? Same convention is being used right here, so that we can come up with these values. You can come up with these values, okay, from this given load. Okay. So if we are talking about moment, this is the critical type of loading. So span 1 and 3 must be 5.1. For example, span number 2 is 2.8. Okay? But if we are talking about shear, so as you can see, 7.9, then the third one is 2.8. Okay? So it is about 30%, okay? About 1/3 of this. Okay? This 7.9. Because of that, these are the what? Maximum positive moment in span. Oh, if you have the maximum at span number 2, this is what will happen compared to that one. Compared to this, okay? Span 1 and 3. So if the maximum moment is span 2, this is what will happen. Okay? So take note of the difference. Almost the same. Huh? Almost the same, but the span number 2, as you can notice here, is what? Below the horizontal line. Here, from this point to this point, everything is below the horizontal line. Okay? But here, from here to this point, there are portions above the horizontal line. Okay? So it's different because we have what? Span number 2. Positive moment. What about this type of loading? Okay? So we have from this point, span 1, span 2, 5.1, then span 3 is 2.8. So what will happen? So like this. Okay? So because of this analyzed already, these combinations are analyzed already and proven by test. Okay? So the result of this various redistribution is actually an envelope of extreme values of moments at critical sections. The envelope for the 3-span beam considered in this section is presented in here. So this is the envelope. What do we mean by envelope? Meaning the envelope, these are the minimum, maximum. So maximum is those values greater than the horizontal, and minimum are those values less than the horizontal. So if you will estimate, a good estimate would be between these envelopes. So these lines are envelopes. So for example, I would estimate it. I will make a diagram that looks like this. That is inside the envelopes. So these are envelopes. Okay. Okay. So the reductions in bending moments because of momentary distribution as described here do not mean that the safety factors for continuous members will be less than those for simple span. Rather, okay, the excess strength that such members have because of discontinuity is reduced so that the overall factors of safety are nearer but not less than. Take note, nearer but not less than those of simple span. Okay? So without the safety being decreased or minimized, so we'll have the very good estimate. Okay, the very good estimate because we are given the envelope. Okay, so that is the suggestion of the code. Therefore, what is the usefulness of this? Preliminary design of members. So immediately we can have a preliminary design and we use that estimate already. Then if you want, you can have a final design. Okay. However, what I experience in the field, the preliminary design will be the final design. Okay? Okay? You can, if you become an engineer, try to observe. They will not change it. The preliminary design estimate will become the final design. Okay? Before an exact analysis of a building frame can be made, it is necessary to estimate the size of the members. Even if a computer design is used, okay? Even if a computer design is used, it is often economically advisable to make some preliminary estimate as to sizes. Okay? So, if an approximate analysis of the structure has been made, it will be possible to make very reasonable member size estimates. The result will be a appreciable saving of both computer time and money. I don't know why we need to save computer time. We need to save human time, not computer time. Okay? But I agree, we need to save money. Okay? Okay. What do you think? Which one do we need to save? Computer time or human time? So an experienced designer can usually make very satisfactory preliminary size estimates based on previous experience. So your previous project, so you can have what? Engineering judgment, what size would it be if a certain load come up? Just like our example, just like our that's why every example here you can actually memorize. I will not say this if our subject is mathematics. If our subject is mathematics, no need to memorize anything. But we are professional subject. Okay? You can actually memorize the subject. Why? Because this will form part of your experience. Okay? So, in the future, when you have when you have this type of loading, you already know that 365, 230, 102, okay, are the maximum, and you have negative 504, negative 260 as the minimum with this kind of loading. So this forms part of your actual experience. Okay, do you follow? Do you follow? Unlike if we are talking about mathematics. Okay, so these values are actually relevant in practice. They are being used in practice. Okay, so if you already have third year and fourth year engineering, actually you can say that you have 2 years of practice if you really put those subject in serious consideration. Okay? If you seriously study those subjects, those professional subjects, you can say, I have a 2 years experience. Okay? As a designer, because we are talking about design. Okay? However, most of the students will not do that. Okay? Because they do not have the seriousness, the necessary study habit. Okay? Because if you already know this and you even have the ability to memorize, unlike myself, I cannot memorize numbers. But if you can memorize numbers, you can actually memorize this. If you have the load 5.1 kilopounds per foot, 2.8 kilopounds per foot, okay, and then you will get this following maximum minimum. Just remember this maximum and minimum. Okay? So that's how we relate. That's how our subjects relate to actual practice. Okay? Are you aware that, for example, Philippine Military Academy, when they enter first year, the first year up to fourth year until they graduate, that is already part of their experience. Do you know that? That is already part of their public service. Okay? While learning from first year to fourth year, that is already part of their public service. Okay? So they will just serve for 16. They will just serve for 16 years plus 4 years in college, that is PMA, then they can retire. Imagine that. Imagine that they can already retire at the age of what? 22 plus 16, 36. At the age of 36, they can retire. At the age of 36 because they already have 20 years in public service. How do I know it? Because my alma mater in Japan, where I graduated engineering, that is what they told us. While you are studying in this school, from first year to fourth year, that is part of your experience. Because we do not have laboratory. We have practice. Okay? The difference between laboratory and practice is very far. Our laboratory equipments are there, but we are doing it like as if we are working. Okay. The motion, the activities, the problem solving that we are working on are real life problems. That's why from first year, same with Philippine Military Academy. Okay? What they are doing from first year is actually part of their service. Same with us. So I can say, we are told by the Japanese government that your stay studying 4 years of engineering or 5 years of engineering is already 5 years of engineering study and 5 years of experience. So, I am getting 5 years of study and 5 years of experience plus 4 years of job. So I can say I have what 8. I can say I have 8 years of experience in Japan. The same is true with what I am telling you. If you can just take it by heart, these numbers, you can say that you have the actual experience, similar to the 2 years experience of engineer after they graduate and after they pass the board exam. Take note. Okay. If you take this by heart, that is the condition. Okay? Because if I ask you a question, you should be able to answer. Okay? So, not only, we are not just counting the years. We are actually counting the real experience. What you get in 1 year. What did you get in 1 year? What did you learn in 1 year? That is how we convert it. What did you get in 1 year? What did you learn? Can you solve this? Oh, yeah. That is the difference of counting by years. Okay? Just counting by years is simple. But counting what you learn is different. Okay? For example, we are going to end our lectures today. What did you learn up to this point in this particular course? It would depend person to person. One person would learn so much and another one would learn 0, for example. Okay? Do you believe that all of you have the same amount of learning? No. Okay? Some may have 50% learning, some may have 30% learning, some may have 10% learning, and some may have 0 learning because just doing the compliance and taking the attendance. Attendance will not get you any learning. Okay? You will not learn anything from attendance. Okay? This is a professional subject. Okay? This forms part of your experience. So what kind of experience? Of course, this is not a construction experience. So there are several experience in our field. And this is an experience for design. This is a design experience. Design of the structural elements. So that is an experience for design. Of course, you don't have experience in the field, construction, but that is another thing in civil engineering. Okay? Design is another thing. So design experience, construction experience, 0, but design experience, you get 2 years. 3rd year, 4th year. If you can only take these concepts and principles by heart. Okay? So, an experienced designer can usually make very satisfactory preliminary design estimate because of this previous experience. Okay? So, for instance, to size columns appropriately, a designer can neglect moments and assume an average axial stress or ultimate force divided by gross area. Okay? This is preliminary. Value of about 0.4 FC prime to 0.6 FC prime. Okay? Take note. Okay? 0.4 FC prime to 0.6 FC prime. Where did you find this? Where can you find this? Where did you get this? Okay? This rough value can be divided into the estimated column load to obtain its estimated area. If moments are large, lower values of average stress, lower meaning take the half of this, so 0.4 to 0.5, okay, that is the half, can be used. If moments are small, higher values, 0.55 to 0.6 can be used. Okay? Immediately, we have the experience. Okay? This is interesting if you take this learning by heart, if you really want to become a civil engineer. Okay? So, if you want to become a real civil engineer, not only a civil engineer by education, by number of years of studying college without learning actually. So there are plenty of students like that. Okay? If we talk of beam rather than column, beam sizes can be obtained by considering their approximate moment. A uniformly loaded simple beam will have a maximum bending moment equal to, take note of this, okay, maximum bending moment, WL squared over 8, whereas a uniformly loaded fixed-ended beam will have a maximum moment of this one. These are from the theory of structure. Okay? For a continuous uniformly loaded beam, the designer might very well estimate the maximum moment somewhere between the values given. So, between these two. Okay? So, continuous between these two. So, what is the between? So, WL squared over 10. That is in between of these two. Okay? And use that value to estimate the beam size. Okay? We can already have. From the theory, we are using the theory as a basis, scientific basis, to have an estimate. Okay? So, what do you mean by this? We have this envelope, we have this envelope, in between, we have our best estimate. Okay? So, for many structure, it is necessary to conduct at least two different analyses. One analysis is made to consider the effect of gravity loads, okay, while another might be made to consider the effects of lateral loads. So, gravity loads and lateral loads. So, lateral loads are those loads that are horizontal or inclined. Okay? So, gravity load, the vertical loads. Okay? So, for gravity loads only, U usually equals 1.2D plus 1.6L. Okay, we already know these things. Because the gravity loads affect only the floor to which they are applied, each floor can be analyzed independently of others. Such is not the case for lateral loads because lateral loads applied anywhere on the frame affect the lateral displacement throughout the frame and thus affect the forces in the frame below. Okay, you cannot do it independently. So, lateral loads is what? More complex. Requires more complex analysis and solution. Okay? So, for this situation, the load factor equations involving lateral forces must be applied. Okay? Sometimes a third analysis should be made. Okay? Not only two analyses. Okay? So, vertical load, lateral load, Third analysis, one that involves the possibility of force reversals on the windward side or even overturning of the structure. Take note of the word overturning. You will encounter this on other design subject. Okay? This is a design technical term. Windward and overturning. If overturning is being considered, the dead live gravity load should be reduced to their smallest possible values in order to allow critical analysis of the structure. Okay? Take note. Overturning. Okay? So, by putting on the minimum to the dead and live load. Okay? So, while the lateral loads are acting, for this case, ACL load factor equation 9.6 and 9.7. You know this. 9.6 is the equation with wind, and 9.7, that is the equation for earthquake. Okay? So, I hope you already memorized those combination of loads. Okay? So, what is the approximate analysis that we can conclude? Okay, according to the code, statically indeterminate structure may be analyzed exactly or approximately. Okay? This is what I'm telling you. Estimate, approximate. Some approximate methods involving the use of simplifying assumptions. Okay? Where? Simplifying assumption. Where did we assume? Okay? Despite the increased use of computers for making exact analysis, approximate methods are used about as much or more than ever for several reasons. Okay, there are several reasons where we are still using approximate one. For example, the structure may be so complicated that no one who has the knowledge to make an exact analysis available, or no suitable software is available. Number two, some structure either method may be subject to so many errors and imperfections that approximate method may yield values as accurate as those obtained with an exact. Okay? So, introduction of so many errors. Okay? So, because of that, the degree of our approximation is on the same or at par with the exact solution. Okay, number 3, to design members of a statically indeterminate structure, it is sometimes necessary to make an estimate of their sizes before structural analysis can begin. Okay? Sometimes necessary to estimate. In what way? For example, initially, preliminary, because we need to determine the dead load. And included in the dead load is the self-weight. Therefore, we need to estimate the dimension of the element initial dimension that we can try so that we can proceed with our exact computation. Okay. Number 4, approximate analysis are quite useful in RAP checking exact solution. We can make a RAP check, for example, to prevent having error in our computer apps. So you have a computer apps, then doing it, then you don't know if you really have that confidence to the result. Okay. So from the discussion of influence lines, you can see that unless a computer is used, an exact analysis involving several different placement of live loads would be a long and tedious affair. For this reason, it is common when a computer is not readily available, and then we will have approximate method of analysis, okay, such as the ACI moment and shear coefficient, so that we will talk about. So these are the recommendation by the code. These are the coefficients that are recommended. Okay? A very common method used for design of continuous reinforced concrete structure involves the use of ACI coefficient. This is what we call ACI coefficient for continuous beam slab. And we can design beam and slab. Okay? We already have the knowledge how to design the exact beam and slab. This is approximate. Another alternative method. So this table is, you can find this table in the code. And as you can see, you have the following. Okay. Positive moment, then negative moment, then negative moment, then negative moment, then negative moment. How many negative moment? 1, 2, 3, 4. There are 4 negative moment and only 1 positive moment. So positive moment usually you can what? You can see those in end spans, okay? End spans or interior spans. Okay? End span meaning the exterior one, okay? The exterior span. So in example of beam here. In this example, this is what we call exterior span. Exterior span because this is the exterior side. Exterior of the building. Exterior of the building, exterior. That's why this is exterior span. Exterior span. This is interior span. So how many spans are there? 1, 2, 3. There are 3 spans. There are 2 exterior spans and 1 interior span. Do you follow? Do you follow? So, for positive moment, for end span, meaning exterior, okay? So, there are 2 conditions. If this continuous end is unrestrained, if this continuous end is integral with the support. What do you mean? Integral with the support. Homogeneous, no? Homogeneous. They are poured at the same time and cured at the same time. So, integral. 1 unit meaning the beam in the support or the slab in the support is literally 1 unit. Okay? So, with these 2 conditions, we have some difference in the coefficient. Okay? So, what do you mean by coefficient? Take note, all of the variables here, WL squared, WL squared, WL squared. Because WL squared is what we mean by moment. WL squared. Okay? The coefficient here is what we mean by this one. 1 over 16, 1 over 24, 1 over 12, 1 over 11, 1 over 10, 1 over 9, 1 over 16, 1 over 14, 1 over 11. Those are the coefficients. Okay? Therefore, if we are on the positive moment, there are 3 different conditions that you can see. Interior span, that is 1 over 16. Right? Where on the span you can see positive. That is about in the middle of the span. That is the positive moment. Okay? 1 over 16 if the span is interior. If the span is exterior or at the end, look at the end if it is unrestrained or if it is integral with the support. Right? So, integrally with the support, 1 over 14. Unrestrained, 1 over 12. So the moment will become larger. This is larger. This is smaller. Okay? The greater the denominator, that is smaller. 1 over 16 is smaller than 1 over 11. So if we have unrestrained, bigger. If we have restrained, too much restrained because it is interior. Okay? It is interior and therefore it is what? Integral with the support. So therefore 1 over 16. So exterior 1 over 14 and for unrestrained 1 over 11. You have to memorize this actually. 1 over 11, 1 over 14, 1 over 16. That those three are the available possibilities for positive moment. What about negative moment? Just like what I told you, 1, 2, 3, 4. So there are 4, and actually, on the first one, negative moment at exterior. Okay, exterior. So what do you mean by exterior face of first interior support? What do you mean by this? Let's take a look at first interior support. Okay, this one. For example, 1, 2, 3, 4. There are 4 columns. Take for example that these are columns. Okay, columns. Okay, columns. Okay. So this is the first interior support. Okay? This is the first interior because this one is exterior. So this is interior, but this is the first one. So this is the second interior support, but if you are looking from this side, this is also first interior because you are looking at this side. So instead of becoming a second interior support, this is also first interior support. First interior support. Okay? So first interior, first interior. So if there is another span here, then this will become second interior support. Okay? So second interior, take that, first interior support. Okay? We know what do we mean by first interior support. Okay? Now, what do we mean by exterior face of first interior support? So there are 2 faces. There are 2 faces. So we are talking of first interior support. There are 2 faces. Exterior face and interior face. So this one. Okay? Do you follow? This one is exterior face. This is interior face. Why it is facing exterior? It is facing outside. Exterior face. This is exterior face because it is facing outside of the building. This is interior face because it is facing inside. So this is what? First interior support. So this is the exterior face of the first interior support. This part. Okay, this part. And what is the moment there? What is the coefficient there? If you have 2 spans, 1 over 9. If you have more than 2 spans, 1 over 10. So let's take a look. In our example, we have more than 2. So therefore, 1 over 10. What is this? Here. You can see? Can you see it? 1 over 10. Okay? The coefficient is 1 over 10. It is negative because it is a negative moment. That's why negative 1 over 10. Do you follow? What about this? Positive. This is what we mean by interior. 1 over 16. 1 over 14. That is what we mean by exterior. So 1 over 14, 1 over 14. Because we have what? Integral. We have integral part. Okay? So For example, this is not a column. Okay? Not a column. But for example, this is cantilever. So, if this is cantilever, this is positive 1 over 11. Do you follow? Do you follow? Because a cantilever is unrestrained. Do you follow? Here. You have what? Here, unrestrained. 1 over 11 positive. Do you follow? So there are only 3 possibilities for positive moment. 1 over 11, 1 over 14, 1 over 16. Oh, sir, why it is not being taught in theory of structure? Because you need to study theory of structure properly. This is estimate, and actually you can use this now because you can use these values to estimate what you already learned in theory of structure. Okay. Okay. So that is for negative 1 over 9 and 1 over 10 for 2 span and for more than 2 span. What about at other phases of interior support? Meaning exterior phase of first interior support, meaning interior phase of interior support. What is the amount? 1 over 11. O, take a look. This is 1 over 11. This is 1 over 11 because it is other phases. This is 1 over 10 because this is exterior phase of first interior support. Do you follow? Do you follow? Okay, do you follow? Then next, negative moment at phase of all supports for A, slab with spans not exceeding 10 feet. Okay? If the span do not exceed 10 feet. In SI unit, that is 3 meters. Okay? If the slab with span not exceeding 3 meters. Okay? Letter B, beams and girders where ratio of sum of column stiffness to beam stiffness, okay, exceed 8 at its end of the span. Ratio. We are talking about ratio. 8 does not exceed or exceed 8 at its end of the span. Beam and girders where ratio of sum of column, that is only for beams and girders. Okay? So letter B is for beams and girders. Letter A is for slab. Take note the difference. Okay? For slab, must be 3 meters span. Okay? For beams and girders, the ratio must not exceed 8. Okay? Ratio of what? Stiffness. Okay? Stiffness. So we are calculating stiffness on our theory of structure. So compare the stiffness ratio must stiffness to beam stiffness, column stiffness to beam stiffness exceed 8 at its end of the span. At its end of the span. So what is the value of coefficient 1 over 12? Okay? So the last negative moment at interior faces, okay, interior faces of exterior support. Okay. First, look for interior support. Rather, exterior support. We already know what is interior support. Very easy to locate where is the exterior support. And look at interior faces. So where are those? I will show you. Where are those? This is the exterior support. This is the exterior support. Where is the interior face? This is the interior face of the exterior support. And therefore, the value is 1 over 24. Here, 1 over 24. 1 over 24. So we are complete. We can actually immediately, just by looking at it, just by looking at the house, Just by looking at the house, by just looking at the what? The structure, we can immediately estimate the moment, positive and negative moment. 1 over 24. 1 over 14. 1 over 16. 1 over 11. 1 over 10. We can already calculate the values of moment. Do you follow? By just looking at it. So this is the exterior support. This is the interior face. Okay, take note ha. Interior face of the exterior support. Okay, that is 1 over 24. Here. Interior face of exterior support. Okay? Where the support is a spandrel or girder. If the support is column, 1 over 16. So, just like I told you, if my condition is okay, this is, if this is column, then this is not 1 over 24. This is 1 over 24 because this is actually beam. Beam support. These four are beam supporting the slab. Okay? But if that is not a beam, but rather a column, the value is 1 over 16 here. Okay? Note the difference. If that is column and not a beam, 1 over 16. 1 over 16 is bigger than 1 over 24. So if there is a beam that supports a slab, so that is better because the moment is smaller, 1 over 24. But if the column directly supports the slab, so that is 1 over 16. Okay. What about shear? So there are two conditions of shear. What are those? WL over 2, WL over 2. So WL over 2 is the amount of shear. That is the magnitude of shear. There are only two types of coefficient, 1.15 and 1. So 1.15 and 1. And members at face of first interior support, at face of all other support. So just need to locate the first interior support, like this one, first interior support. Okay, shear in end members. Okay, end members. So take note, 1.15. Okay, these are moments. So we can take a look at the shear. Where are the shear? So there is no shear, no? So if ever there is a shear, we have the first interior support. Okay, these are the first interior support. Okay, so the first interior support. Okay, end members at face of first interior support. So meaning to say, the shear here, and the shear here. So there, this is only for moment, no? There is no shear. So that is 1.15 times WL over 2. And that is the shear. Okay? Do you follow? Do you follow everything? So we can have an example. Okay, we can have an example. But before we have an example, let's stop our discussion and just return back to the live stream in order to cut the video. Okay, so let us cut the video. If you have any question, so let's initially cut the video. And there are only 10 students, so there are no question. There are only 10 students that are listening, okay, that are here. And there are so many, okay? There are so many who just showed attendance, okay? There are so many of you who just showed attendance, and afterwards, there are only 10 of you who are really interested. Okay, so okay, so let us stop it right here and see you on the next live stream. Again, this is Dr. RIPbE